Okay, so now that we have finished up the sample problems in the first, if you would, or the sample problems in the first two sections, you would be able to work on the following problems as we see here as far as your application problems. But we still have more work to do tonight, and we're just kind of finished up this first PowerPoint. So what I'm going to do now is go back to our module, to our learning plan. And I'm going to pull up in that same sense. We're going to start on part 2 now, kind of cross over. And we are going to do the next sample problem, which is sample problem 11.6. 11.6. And we're, like I said, we're going to do this one together. So I am going to go underneath my camera and we are going to look at the problem statement. Okay. So this problem starts on page 642. Okay, and here is problem 11.6. So if you're following along in the textbook, 642. So sample problem 11.6 here. In this case, we're going to be looking at two cars. Car A is traveling at a constant 90 miles per hour. Okay, and car A is on the left-hand side here. And when it passes a parked police car, okay, who is going to chase it. And what's going to happen is that officer is going to accelerate at a constant rate until it reaches 105 miles per hour. Thereafter, the officer's speed is going to remain constant. And what we want to know here is we want to know what is the initial acceleration of that police car when it catches it 3 miles down the road, the other car, the car A. Okay, so you have an illustration here of these two cars. So on the left-hand side, this is going to be like our origin. So this would have been where car A passes the police car, okay? And what's going to happen is that car then is going to, the police car then is going to take off. So this, the car A is going to continue at a constant velocity. It's not going to speed up or slow down. It's just going to stay at that same 90 miles per hour. And then the police car, starting from rest now, is going to accelerate. Now you're going to notice that there is this intermittent time here. This is time 1. This is going to be the time that the officer accelerates. And at this point, the officer is going to be at that 105 miles per hour. Okay. Then what's going to happen after the officer hits 105 miles per hour? The officer is going to go at a constant rate until catching up with the car itself. And that point is going to be at the 3 mile mark. Okay, so again, what we want to know for this problem is what was the acceleration of the police car, which would have been during this time frame right here, this section. Okay, right. So let's first write down what we're given and the conditions that we're under for each one of the cars, and then we'll proceed to do our solution. So I'm going to put this away for a second, and we'll come back to it. But, so this is sample 11.6, okay? And again, we're going to start with car A. Car A. So this is the actual car that's going 90 miles per hour. Now, the condition that this is under for the entire time is it is going to have a constant velocity or uniform motion, as the book refers to it. So we know that the original and final for the velocity of point A is going to be 90 miles per hour. Okay. And it is going positive because it's going to the right. Okay, so we're going to use kind of that standard convention. Since we're in a horizontal motion, it's going to be to the right is positive. Our acceleration then of car A, because it's going at a constant velocity, is going to be 0. Okay. We also know that the final distance for A, so I'm going to call it XAF, the final distance, is going to be 3 miles. Okay. Now for car B, we're going to call that car B, but it's the police car. Car B. This is going to be constant acceleration. Okay. for the first part. So there's going to be two phases that this car goes through. So from a time equals 0 to T1, and we don't know what T1 is yet. So if we go back over here underneath, remember they have T1. This is the time when the police car is accelerating to 105 miles per hour. Okay. So during this time frame right here, our velocity original of that police car, so VOB, is 0 because it's starting from rest. And the V final B, okay, is going to be 105 miles per hour. Okay. So when we get to that time 1, it's going to be going 105 miles per hour. We want to find what is this acceleration. That's going to be what we don't know that right now. Okay. Because we don't know the time, right? We do know the change in velocity, but this is what we're going to be working on. Okay. We also are going to need to know for this phase what our X1 is. Okay. What is our X1? So for instance, from here, from rest to when it stops accelerating, when that police car stops accelerating, when it gets to 105, what was that distance? And we're calling that X1, which is consistent with the illustration here. If you can see that, that's X1. Okay. So this is T1, this is X1. So this is going to be the distance that it takes to get to 105 miles per hour. And then there's going to be the second phase that our police car goes through. Okay, so I'm going to put a little line here, and this is going to be from T1 to the overall time. Okay, T. I think that's right. Let me just double check. Yeah. And that's the total time to get to the end. So our T is going to be from 0 all the way to when they catch each other. So T1 is the intermittent and T is over here. Okay. So from when the police car stops accelerating, now the police car is going to have constant velocity. Okay. So what that means is during this time frame, the acceleration of that police car is equal to 0. Okay. And then the overall to the final, the distance B final, because they're going to catch each other, is going to be the same here. So this is going to be 3 miles. Okay. So those are our givens. Now, I just want to identify, I want to find, so we're only finding one thing. We want to know what AB is. What is this acceleration right here? What is the acceleration of the police car when it's speeding up from rest to 105 miles per hour? Okay. Now, as we look here, we've got miles, we've got hours. When we're dealing with English units, we want to have all of our distances and times in feet and seconds. Okay. So we're going to want to, before we get into, setting up the equations and the relationships, we need to do some conversions here. Okay. So we're going to convert the velocity of car A, the 90 miles per hour, to feet per second. We're also going to convert the final velocity of our police car from 105 miles per hour to feet per second. And then as long as we're here doing conversions, we want to convert the 3 miles to feet. Okay. So that's going to, if you would, that's going to be the first step that we're going to do. Because once we have those in consistent units, then we can not worry about having to put those units in our equations and in our work, and just make sure that we add them at the end, and we're going to have everything in feet per second. Okay. So velocity original A is equal to 90. Okay. Now to convert this, we're going to put miles on top per, right? And then this is going to be hours on the bottom. So you have to expand out. Don't write MPH after it. It has to be miles on top and hours on the bottom. And now we want to get this to feet per second. So in 1 mile, there are 50 to 80 feet, right? Miles cancel out top to bottom. And now I need to get my hours to second. There's 3,600. Oh, sorry. 3,600 goes on the bottom. My hours are on the bottom here. So my hour goes on top here. So 1 hour is equal to 3,600 seconds. So what's not crossed out is feet per second. So my velocity in feet per second for A is going to be 132 feet per second. So double check that to be sure that's what you get. So I'm just going to kind of write that there. Then you're going to do the same thing for the velocity of car B. Now this is its final velocity. This is going from rest to 105, and we want to convert the 105. I'm noticing that there's here. Oh, thank you, James, for confirming. I'll actually add that, bring that out again. I like having the chat box. So this one's going to be 105 miles per hour. And then we're going to use the same values that we see here. So 50 to 80 feet divided by 1 mile. Miles cancel. 1 hour is 3,600 seconds. So you should get for this one as well, 154 feet per second is equal to the final velocity of B. Guess I have it as FB on top. I should be consistent. FB here. Final for B here. Because up here, I use FB, not BF. And then the third one that we want to do is we want to get our 3 miles into feet. So that'll just be a quick conversion there. So our XAF or XBF, I'm just going to say XF for the final because it can be either A or B. It's going to be 3 miles. And I simply want to convert that to feet. So 1 mile, 50 to 80 feet. So that means that we have, let's cancel, 15,840 feet is equal to our final distance. Right, when they catch up to each other, that 3 mile mark. All right, so now we have consistent units. So we're going to be using these values then as we go through. And so our distances will all be feet and our times will all be seconds. Okay. So the next thing we want to do is we want to look at each one of these motions separately, just like we did in the previous problem. So we're going to look at car A, and then we're going to look at car B. Okay, and we're probably going to, see some things, pulling things together. So I'm going to go to my next page here, and we're going to look at the motion of car A first. So motion car A. Okay, and as we said earlier, this is going to be uniform motion, which again, I call it constant velocity. But again, the book uses uniform motion as how they describe it. Same thing, they're equal. So because of that, we are then going to, where's my, lost my equation sheet. Oh, here it is. So because of that, we are going to use, and again, I have my motion, my uniform motion, V is constant. These are the 3 equations here. Okay, so I want to identify my value of X in terms of time. So we're going to use this one right here. So this is going to be XA. Okay, it's going to be equal to, and that is going to be the original XA plus the velocity original of A times the time that passes. Now we don't know, see, we're trying to determine, if you would, we want to know what is the time when I get to that 3 mile mark, because we want to know, when that happens. So in this case, we know that where we're trying to go is 3 miles, right? So this is its final X distance. So this is going to be our 3 miles, or the value that we just calculated was 15,840 feet, right? Is going to be equal to, now this is going to be from our origin. Are we looking at this car at any offset distance? And we're not. It's starting at origin 0. So this is going to actually be 0 for us. And the original velocity of A, okay, was 90 miles per hour, but we converted, and VA, if you remember, is 132 feet per second. So that means that our V original A is 132. Now it remains the same second after second after second, but that's going to be its value that it starts out at. And then the amount of time that passes, we don't know. So we're just going to leave that. And I have a bad habit. It's really not a bad habit, but I'm going to take my feet off so I'm consistent through here. So it simplifies the math that we're looking at. So you're going to notice here that our only unknown variable is T. So we can find out how long it takes car A to get all the way to that 3 mile mark. Okay, and that's going to be our total time that we're going to have for this, if you would, that encounter. Okay, so we're going to solve for T here. T is going to be equal to, we're going to take 132 divided on both sides. So 15,840 divided by 132. Our time is going to be 120. You can add the seconds there. It's going to be 120 seconds for the total time from when that car passes the police officer to when the police officer catches up, 3 miles. Okay. So this is gonna come in handy. So now we are going to look at the motion of car B, or the police car. Okay. And we know that car B has 2 phases. Okay. Remember the first chunk, I'm going to bring the illustration back. The first chunk for our police car is going to be where the police car is accelerating to 105 miles per hour. Okay. That's going to be to time 1 corresponding to distance 1, or X1. And then we already know the overall distance is 3, but at that point, they're going to catch up to one another. So we're going to look first at when we are in this constant acceleration phase. And then we're going to look separately at when we are in the constant velocity phase, because this is when he, stops accelerating, and he's going to coast, if you would, at the 105 all the way to when catches up. Okay. So we have to divide that into 2 sections, just like we did when we did our knowns. So for instance, at the top here, when we did the car B, these were the phase between 0 and time 1, which is constant acceleration. So these are going to be the variables that we use on that side. So that's what I'm going to start with. So this is going to be my constant acceleration, which is going to be time 0. Sorry, time equals to 0 to T1. All right, so it's starting from the start to that first point. Now, we know that the acceleration of car B here is what we have to find. Okay, so that's going to be an unknown. We also know that its original from start velocity is 0, but its final velocity is going to be what it speeds up to. Now, it was 105 miles per hour, but we want to use the 154, okay? And we're going to leave the units off here, 154. Now, for this section then, we know that we're going to end with 154, but what we want to do is we want to find the time, or we want to find this velocity in terms of the time and the acceleration. So we can say that the velocity FV is going to be equal to the original velocity of point B, which we know that the police officer started out from rest. So that's going to be 0 plus the acceleration of car B times time 1. Because remember, this is only occurring in that first chunk, that first section. Okay, and then we have to square, we square that? No, that we're in the velocity. We don't square it. So it's just A times T. So we know that the final velocity of B is 154. So we can set this equal to 154 is equal to the acceleration of B times T1. Okay. And we're just going to kind of let that sit, okay? Because we'll have an opportunity in a little bit to use that. So we're just going to put our little cloud around it, or I'm going to put my cloud around it because then I know where it is when I want to find it. During the same phase, we want to know how far did we go during that constant acceleration to time 1, okay? So we're going to say X B1 or X1. And this is, I just have the B in there because the car is car B. It's going to be equal to, now again, this is constant acceleration. So if we look at our equation sheet, it's this equation right here, the second one. It's going to be the X original of B. That happens to be 0 because we're starting at that origin on that left-hand side. So that's going to be 0 plus the velocity original of B times T, again, 0 because the police car is starting from rest, plus 1/2 AB T1 squared because we're in that constant acceleration phase. Okay. So we can say that X B1, and again, it's that X1, it's that distance as we're getting to 105 miles per hour, is going to be equal to what's left here is 1/2 AB times T1 squared. Okay. So we're just going to kind of let that sit as well. Now, over on the right-hand side, let's look at the second phase that we see for our police car. The second phase that we see for our police car is going to be the constant velocity phase. Okay. And this is going to be from T1 to the overall T, like to the end of our 3-mile mark. Okay. Now we already know what this time is. Okay. We know that to be 120 from right above here, right? See, right here it is. Okay. So we know this to be 120 seconds, right? Because that's, we already calculated that because we knew that our car A was going at a constant rate for 3 miles. Okay. So that's already known. Now we want to figure out what is going to be the distance of the car as it travels this section here. So we can say that XB2, and that XB2 is going to be this little distance right here. All right. And that is going to be equal to the velocity of B final. This is when it gets to its 105, but it's the 154 feet per second times the time. Okay. And we know this time to be the ending time, 120. That's what we're going to put in there, minus T1. And we don't know what T1 is yet, but we know this value. So we can say that XB2, okay, that little chunk in there is going to be equal to 154 times 120. That's the seconds for the total time to the end of the 3 miles minus T1. Or one more time, XB2, we're gonna distribute that. That's going to be equal to 18,480, these two together, minus 154 T1. I'm gonna let that sit. Okay. Now, as we look here, I just want to remind us what we have. I'm going to put this up here. So we know that we have our origin where we started. We know at the end here, we have the 3 miles, which is equal to 15,840 feet, right? In between there, we've got a distance. I'm going to kind of call it right here. This distance right here is going to be our XB1 from here to here, okay? And our XB2 going to go from here to here, right? So this was when our police car was 0. This was when our police car was 105 miles per hour. Actually, I'm going to put the feet, hold on. 154 feet per second. And then this is our 3 mile mark where we catch up to each other. Okay. So now when we look at this overall, okay, from here to here, we know it's 3 miles. We know this is the first chunk of the police car, and this is the second chunk. So what we're going to do is we know that our overall, we're going to call this XB, is equal to XB1 plus XB2. And we know XB to be 15,840. So, I kind of write big. I can say that XB, which is the overall to 3 miles, is equal to XB1 plus XB2. Now, so where we're going to do our substitution. So I know that XB, that's the 3 miles, is 15,840. Okay, no units. It's going to be equal to XB1. We know XB1 is 1/2 AB T1 squared. That in there. This is going to be 1/2 AB, the acceleration of that car during that phase, times T1 squared. Plus our XB2. XB2 is this part right here. Okay. So this is going to be plus 18,480. Be careful. 15,840 and 18,480. They're just a little too close for me. So be careful not to, mix those up. Minus 154 T1. Okay. So now we've got some things that we can combine, right? So we've got 2 constants here that we can combine. So I'm going to put those 2 together. And then you're probably already noticing we've got our T1 squared and we've got our T1, right? So there's a good chance that we might be able to take advantage of that. Maybe. We'll see. We'll see. So what I'm going to do is I'm going to move this to the other side. It's going to be equal to 1/2 AB T1 squared plus, I'm going to subtract that off. And that number should come out to be 2640. Okay. And then I'm going to have my minus 154 T1. Oh, I see. No, we're not going to use the quadratic. We have another way we can get it directly. Show you in just a second. So make sure that you have 0 is equal to, when you combine these 2, we're going to subtract 15,840 minus 18,480 should get 2640. Okay. Now what we're going to do, if you recall early on, we solved for the acceleration of AB, or we had it in terms of T. So if we go back over here on the right-hand side for motion car B, we have this 154 is equal to AB times T1. If we rearrange this equation, okay, so for instance, if we solve for AB is going to be equal to 154 divided by T1, right? Just rearranging it and solving for AB. So if I know that this is what AB is equal to, I can take and put that right here. So this is going to be equal to 1/2 times 154 divided by T1 times T1 squared plus 2640 minus 154 T1. Okay, everybody see how I got that? Now, as you can see, when I multiply T1 squared times 154 over T1, one of these T1s cancel, just one of these. Remember, this is T1 times T1. So now what we end up having here is 77 T1 left over plus 2640 minus 154 T1. Now you can see, and I'm sorry, this is 0 over here. I want to keep that 0 there. Now we've got a little combining that we can do. We can take the negative 154 plus 77. That's going to be a negative 77 T1. And then I'm going to take this 2640. I'm going to put it back on the other side, and that's going to become a negative 2640. We can make both those sides positive now, and our only unknown is T1. So yeah, we don't need a quadratic for this one by doing this substitution right there. So now solving for T1, I'm going to divide both sides by 77. Our T1 is equal to, this is going to be 34.3 seconds. Okay. Want to give you a chance to get that and make sure you kind of got this process here to get to T1. All right. So now that we have our T1, that means that we can calculate our acceleration in this time frame. Okay. So we're going to use that relationship that we just had inserted. What that is again. And then, so we know, oh, somebody has their background on. I'm just hearing like humming in the background. So we know that we have this equation right here. And so if we know what the time is, we can solve for our AB, right? So we can simply say that AB, the acceleration of that police car, is going to be equal to 154 divided by T1. So we're going to insert that there. So 154 divided by 34.3 seconds. Our AB should come out to be 4.49 meters per second squared. Again, magically appearing here, but because we've used meters and seconds throughout, these will be our final units. Hold on, Christian. For those who are at this point, did you get the 4.49? This is the final answer then, okay? All right. So what I'm going to do, are there any questions at this point? And I will go back, Christian, in just a second. Are there any questions on the problem? What I'm going to do is I'm just going to do a quick review of what we did. So looking at the very beginning, we looked at car A and car B with the conditions that were present. We were using feet. I'm sorry, Tanner, you're so right. So it would be feet per second squared at the end. Sorry about that. Yes, we were. Yeah, I've been working 6 different problems the last couple days. So thank you. I'll get that updated when I get to the end there. So our 2 conditions here, we did our conversions to start off with to get into feet and seconds. Yep. Then what happened was we looked at the motion of car A and we solved for the overall time to get to the 3-mile mark. Then we looked at the motion of car B and split it into its first section where it had constant acceleration and its second section when it had constant velocity. Okay. Then we took the distances for the overall distance of 3 miles. And then we added the 2, the XB1 and the XB2, giving their equivalent equations. And then what we did was we saw that we had AB, the acceleration of car B, times T1 in our problem. But because we had identified AB in terms of T, we could do this substitution at this point right here, okay? And then we got down to a common variable of T1, and then solving for our T1, 34.3 seconds. That's the time that we're going at the constant that we're accelerating with that police car. And I'm going to fix my units here. It's feet per second squared, and using that value back into the acceleration B for that police car during the time 1, we get the acceleration of that police car during that section of time at 4.49 feet per second squared.